Hello guys, welcome back to my YouTube channel. I'm Naftal. In today's lecture, we want to talk about inductors and inductance. Inductors and inductance. So I'm going to start by defining what is an inductor, and we define later what is an inductance. So an inductor, I'm going to say, is a device used for storing energy in a magnetic field. A device that is used to store energy in a magnetic field. That is, if that device is placed in a magnetic field, it's going to store energy in terms of magnetic fields. Now, let's start with those devices that can be used as inductors, those that can be able to store energy once they are placed in a magnetic field. So one is a coil. And we know a coil as a current carrying material that is wound on a cylindrical material to make a number of turns. Now consider this diagram. This is a wire that will be wound to this cylindrical material to make the coil. Now this is the direction of our current. Current is moving in this direction and getting out in that direction. Now we have said that once we have this material, this is our coil, and once we place it in a magnetic field, it's going to store energy. Now I want to put magnetic fields, and this is the direction of our magnetic fields. They are originating from this point and ending at this end. Those are magnetic fields. Now, this is a closed magnetic field. Remember, we have said an inductor is made when we place an inductor is a device that can be able to store energy once it is placed in a magnetic field, and the energy, we are going to see it later, it will be stored in terms of magnetic fields. Now when these lines, each of them, or if one line passes through the center of this coil or of our solenoid, it's going to induce current any times. That is where n is the number of turns. So we are going to say that each line that passes through the center of our solenoid, will induce current n times, where n is the number of turns. And if all the magnetic fields passes through the center, it's going to link. Now, so if all the magnetic fields are going to pass through the center of our solenoid, it's going to give us the total magnetic flux linkage. And I'm going to say that is if all the magnetic field lines pass through the center of the solenoid, it will give total magnetic flux linkage. And the symbol for magnetic flux linkage we normally use this one. This is magnetic flux linkage, and we have said it will give us, and this is the formula for magnetic flux linkage, that is the number of turns times the magnetic moment. That is the dipole moment. This is the dipole moment times the number of turns. Now, by definition, we are going to say, now we want to define what is inductance. We have defined what is an inductor, and we have said when we have a magnetic field, when they pass through the center of the solenoid, it's going to give the magnetic flux linkage. Now we want to define what is an inductance, and I'm going to say inductance, and we use this symbol. This is the symbol for inductance, is the ratio of the total magnetic flux linkage to current. Now, I'm saying, so inductance is equal to magnetic flux linkage over current. Now, in differential form, remember, the current is going to change depending on the number of turns the magnetic field are going to pass through. Therefore, we can say our current will be changing with the time and the dipole moment. Therefore, we can say in differential form, of course, the number of turns will remain to be constant. Remember, we had said where our magnetic flux linkage is equal to the number of turns times dipole moment over current. That is the formula. Now, the number of turns n will remain constant, and therefore the factors that will be changing is the dipole moment and the current, and therefore we will say d psi over di. Those are the factors that are going to change as the process continues. Now, we have to let's look about inductance of simple geometries. Inductance of simple geometries. Now, the first thing we're going to start with is a solenoid, and we have been using a solenoid in our case to define what is an inductor and what is an inductance. Now, let's look upon those devices. Now we're calling them as geometries in our case here. Now, the first one, we're going to say the inductance of a solenoid. So, the first geometry is inductance of a solenoid. Now, since the voltage of the connecting current, remember in our diagram we had said we are going to connect our solenoid. This is the movement of current, meaning there is a voltage that is going to be used. Now, this voltage remains constant inside the solenoid. Therefore, we can say the magnetic field lines will be equal to mu, the number of turns times current over length. Now, remember this formula, we derived it from when we were calculating from the Ampere's law of the closed circuit. Now, we want to say this, that magnetic flux linkage that we had said as the number of turns times the dipole moment will be equal to, this is the number of turns times the magnetic magnetic field lines times the area, that they are equal. Now, we want to derive the formula for inductance for such a solenoid, and having said this is the relationship that we have, this formula is equal to this one. Now, this formula, remember this formula and this one were derived in the previous video that I had posted. Now, we'll say that inductance will, now this is having that we said the value for B is this one. We want to insert B in here or here because the two are equal. So I'm going to say magnetic flux linkage will be equal to this is the value for B, this one, times NA. This is NA, and we are going to get this is mu N squared I, which is current, times the area over length, the length of the solenoid. Now, and we redefined in, we said the inductance equals to magnetic flux linkage over current. Now, our will be equal to magnetic flux linkage over current, and our magnetic flux linkage we have calculated as mu N squared times current times area over the length times current. Now, this current and this current will cancel out, and therefore we are going to say the inductance for a solenoid is given by mu N squared times area over length. Now, let's do an example to see whether we have understood that concept. And we say this is our example 1. Example 1. Now, compute the inductance of a solenoid with 200 turns wound uniformly over a length of 500 millimeters on a cylindrical paper tube of 40 millimeters in diameter, given that the medium is air, and the medium, that is the permittivity of air, is equal to that of a free space. We are going to say, in our case, we take to be equal to that of free space, and this will be our working third example. And we are going to say inductance, we decide, is equal to mu N squared times area over length. Now, our mu, we have been told, this is the permittivity of air, and we have been told is equal to that of free space. Now, that is the permittivity of free space times the number of turns squared times the area over the length, which will be equal to, the permittivity of free space is 4 pi times 10 raised to power negative 7 farads per meter times 2000 squared times the area for our solenoid will be 3.14 times 40 over 2 times 10 raised to power negative 3. That is to change it into meters, and this was our diameter, and I've divided by 2 to give us the radius over the length, and the length we have been told is 500 millimeters, and we want to be into meters, and the answer for our case will be equal to 3.1567 times 10 raised to power negative 3 Henry. And the formula for the unities for magnetic for inductance is Henry. that we give it H. So let's talk about the inductance of a toroid. Inductance, that is for geometry number 2, inductance of a toroid. And we had defined what is a toroid, and we had said a toroid is a device, or we're going to wound our solenoid in a circular material in a number of turns. So if you have a solenoid and you wound it in a cylindrical material, you make a toroid. So a toroid is a substance that is made when we wound a solenoid in a circular path in a number of turns. Now, consider the case. So when a solenoid has a uniform windings, that is the windings are in uniform, the magnetic field will be confined to the interior of the winding, and we are going to say the magnetic density to be equal to 0. That is, if we have our fields are originating and ending on the same point. Remember, we had said in lamellar fields, when we have lamellar fields, when they originate and end in the same point, the magnetic density will be equal to 0. But now, consider this is to be our toroid. I want to draw our toroid. This is the circular path I was saying. And we have our, take now this one to be our solenoid. We are winding the solenoid on this circular path. We want to make something of this nature. Now, having this is current in and this is current out. Now, from this point to the center, that is the center of the solenoid, to this point is the radius of our solenoid. And these are the number of turns I was talking about, and of course this is current. Now, if we say that the radius of the toroid is much greater, or we can say is larger than the radius of the solenoid, that is the ratio between the radius of the toroid and the radius of the solenoid is large, we can say this will be our case. Now we are going to have a real case, and we will say, from our formula we had said magnetic flux linkage is equal to the number of turns times magnetic dipole, which is equal to the number of turns times magnetic field density times the area. But so we had said it will be equal to that formula that we had generated will be equal to mu n squared times current times the area, but the area in this case will be the area of the solenoid, which will be equal to pi, and the area of the solenoid is pi r squared. Now r, we take the r small for the solenoid over the length, and the length here we're going to take the length of the solenoid, and how do we find the length? It's like the circumference of the toroid, which is 2 pi r. Now pi and pi will cancel, pi and pi will cancel, and we will form magnetic flux linkage to be equal to mu n squared times current times r squared over 2r. That will be the formula. Now, we wanted to calculate the inductance, and the inductance we had said is magnetic flux linkage over current, which will be equal to, this is the magnetic flux linkage mu n squared times current r squared over 2 r times current. Now this one and this one will cancel out, and we will say that our inductance for the toroid will be equal to mu n squared r squared over 2r. That is the formula for inductance of toroid. Now, the second case we will talk about, sorry, the third case is, our third case is the inductance of a coaxial wire. The inductance of a coaxial wire. And we had talked about the coaxial wire when we were calculating the potential of a dipole from a distance, and we said a coaxial wire can be used or can be said to be a dipole from a particular point if we consider it, and that is the time we made this word, the coaxial wire, and you know it mostly is used in television cables and the radio cables. Now, this is we take this as a coaxial wire will be of this nature, and we'll say, remember, it has the outer cable and the inner one, and this is the outer layer. Now from this point to this point will be the radius of our cable, and I will say is equal to b, and from this point to this point we'll say is the radius for the inner wire, which is a, and from here to here will be the distance between the center of the inner wire to the potential, which we are going to give it as r. Now, from Ampere's law, we said that the closed field when magnetic field lines are passing is equal to mu times current. That is, if we differentiate this part, we complete this part will be 2 by times 2 by, that is b times 2 by r will be equal to mu I. Remember, how did I get these 2 by? Some may be asking, how did it come about? Now this is the, before this is our formula we're interested in, but let me expound on this. How did I get this from? Now, take that the closed integral for b to dl is equal to, and we have said is mu times current. Now, this is the surface integral, but it is closed. Now, our coaxial wire will be having a length, and the length is the one that is changing. Now, when we calculate, this is b is constant, so it can come out, and we find the integral for dl. This one can be equal to, like we are finding the length for that closed path. That is like saying the circumference for that path, which can be equal to 2 pi r. And remember, this is the formula for the circumference, and that is the length. We are calculating the length of our coaxial wire that we said, or could be the in here or out here. Remember, we are calculating the length, and the length in our case can be taken as the circumference, will be equal to mu times current. Now, I want to make be the subject of the formula, so divide by 2 by r, divide by 2 by r, so it will be equal to mu I over 2 by r. Now, that is the formula for magnetic field density in a coaxial wire. But what we are interested to calculate is the inductance for that wire. Now, let's see the total flux linkage for such a wire. Now, consider our coaxial wire to be having a length d. Let's take it our length to be d. Now the flux linkage to this coaxial wire will be equal to d over the integral from the distance a to d. Remember, we had said the length to be having length d from, now we take the limits from a to d. Now we'll times b dr. Now that is the flux linkage. Remember, we said once we have a magnetic field, when they pass through that inductor material, it's going to cause flux, magnetic linkage, and that is what we are saying here. This is the magnetic field line are passing through our inductor, and in this case it is a coaxial wire. Now it's going to induce this magnetic flux linkage. Now when we work out this part, it will become d is equal to, I remember we took this limit to be a to b. Sorry, here we said a to b, and this is the length for that material, and the length, remember, will remain constant. D will remain constant, and we bring it outside the integral. That's why already in my first case I had already brought it outside. Now, and then we'll say from a to b, but we had calculated the value for b, and we had said it to be equal to mu I over 2 by r times dr. Now this part represents the magnetic field lines, which will be equal to d, the integral of a to b. Now this part of here is constant. Remember, mu, the current, and the 2 by are constant, so we can bring them outside. So let's bring them outside. D times mu I over 2 by into the integral of a to b from the distance of dr, the dr over d, dr over r. Now we continue. When we work out this part, we will see that here it's like 1 over r. Remember, when we integrate dr, it becomes like, when you integrate dx, it becomes 1. The same here applies. When we integrate dr, it becomes 1, so it will be like 1 over r, and 1 over r is ln of r. Now we'll say that our flux linkage will be equal to let me look at it again. It will be equal to d mu times current over 2 by ln of r from the limits a to b. Now we'll be having this when we insert the limits to our formula. It will be, the magnetic flux linkage will be equal to d times mu times current over 2 by ln of r b minus ln of ra. Now this can be worked out to become the ln of, this is like minus, and when we in laws of mathematics, when we subtract a log from a natural log from another natural log, can be a division. That is b over a. Now when remember, mu is equal to the permittivity of free space times the relative permittivity, which can be equal to our magnetic flux linkage will be equal to d mu naught times mu, that is the relative permittivity, times current over 2 by times the ln of B over A. Now, this mu naught is a constant that is known, which is 4 pi times 7 raised to power negative 7 farads per meter. Now, when we bring it in here, it will be D, that is the magnetic flux linkage, will be equal to D times 4 pi times 7 times 10 raised to power negative 7 times mu r times current over 2 pi times ln of B over A. Now this can cancel here, 2 times 10 raised to power negative 17. So our new formula will be equal to 2 times 10 raised to power negative 7 d mu r I ln of B to A. That is the magnetic flux linkage, but we were calculating the inductance, and inductance is equal to magnetic flux linkage over current, which is equal to 2 times 10 raised to power negative 7 d r ln of this one over current. Sorry, there is current here, I've forgotten it out. Now this current and this current will cancel out once times, and will be equal to 2 times 10 raised to power negative 7 d mu r ln of A to B. Now, the inductance per meter, that is per distance, per length, the inductance per length of that coaxial wire will be equal to, if that one I divide here, such that our D and our D will cancel out, it will be 2 times 10 raised to power negative 7 mu r ln of B to A. That is the formula for the current, that is the formula for inductance of a coaxial wire. Now let's deal with the coaxial wire of two wires, two transmission wires. That is our case number 4. So we have two inductance, the inductance of two wires transmission, lines, or we can say the inductance of two parallel wires. Now that is the case we want to consider right here. Consider this case. When we have the two wires that we have said, we'll consider them being used as inductors, and we have the current that is moving out of the paper. Remember, when I put this dot here and I circle it, it means it is current that is moving out of the paper. And when I put this dot once and I don't circle it, it means those are magnetic field lines. But when I circle them, it means it is current. Now when I put this dot here, it means that this is the symbol showing us that current is coming out of the paper. And when I put this cross here and I circle it, it means that current is moving into the paper. Now let's see the inductance of such a wire. Now we'll say, remember we defined that when we have at any distance r, we're considering the inductance will be from a particular distance r. Now at any distance r, we'll be having magnetic field lines as remember we stated the formula earlier to be mu times current over 2 pi times r. That is the distance. That is we're considering if we have these two wires from a particular distance. Let's say it is r. Now, we'll say that the total flux linkage due to the two wires for a length. Now, we take the length for such two wires to be d. Now, we say if we consider the total flux linkage due to the two wires of length d, we will say, let's use a small d for that length, and we will say that the magnetic flux linkage will be equal to, remember there are two wires, each will be containing a length d, therefore we say it is 2d, and the integral from the distance a to d, these are the limits for our case here, b, the r, and we decide that the b, that is the magnetic field lines, have this formula, are equal to this one, and I can add them in. I say 2 pi, and the from the limits a to d, then mu I times 2 pi r dr. Now mu I and the 2 pi are constants, so we can bring them out of the paper, so out of the integral. So magnetic flux linkage will be equal to 2d. We bring them out, those are constants. From a to d, dr over r, and I said the r over r is like when we integrate it, it becomes 1 over r. Now it will be equal to 2d mu times current over 2 pi ln of r from the limits a to d. Now when we insert the limits, it will become 2d mu times current over 2 pi ln of d minus ln of, this is d minus a. Now this can be rewritten as 2d mu times current over 2 pi ln of d over a. That is our flux linkage. Remember that this is our flux linkage, that is the total flux linkage, and we decide that the inductance is equal to the total flux linkage over current, and the total flux linkage is 2d times mu times I over 2 pi ln of, that's the natural log of d over a, the natural log of d over a times current. So this current will cancel with this current, and we are going to say our inductance will be equal to 2d, and these two will cancel out, so we'll be having d mu ln of, that's a natural log of d over a pi. Now if I say inductance per that distance, that is per unit length, will be equal to mu over pi natural log of a over d, and we will conclude our case by saying that permittivity is normally equal to relative permittivity times the permittivity of free space. From this formula that we have derived, we want to write in terms of when we have this, we want to replace this permittivity of that material with the relative permittivity times the permittivity of free space is equal to that permittivity. Now the inductance by unit length will be equal to relative permittivity times permittivity of free space over pi ln of d, that's the natural log of d over a. But we know permittivity of free space to be 4 pi times 10 raised to power negative 7 farads per meter. Now it will be equal to, that is our inductance per unit length will be equal to 4 pi times 7 raised to power negative 7, the relative permittivity over pi times the natural log of d to a. Now this pi and this pi will cancel out. Now we'll be having our formula is 4 times 10 raised to power negative 7, the natural, that is the relative permittivity, the natural log of d over dA, and that is the inductance of two wires in a transmission line. Now let's consider the energy of that an inductor. We have discussed the inductance of various materials. We have calculated their respective inductances. Now let's calculate the energy in that of an inductor. Energy of the inductor. How do we calculate the energy of an inductor? The energy of an inductor. Now this energy will be calculated as, consider this diagram here. This circuit. And this is the source of power supply. This is the switch. This is the bulb. This is the voltmeter. And this is our inductor. Now, when the switch is closed, so we can say when, let me call the switch as S. So when S is closed, the bulb lights. Now, when S is open, the bulb decreases in brightness momentarily. The bulb decreases in brightness momentarily. Now this means that this bulb could have went off just once, but we see it going off momentarily. In the next video, I'm going to show that how that bulb is going to behave and how the brightness decreases momentarily. Now, this implies that there is energy that is stored in our inductor, which is giving this bulb the energy to cause it light for such a short time. Now let's calculate the energy delivered to the bulb when the switch is open. Now we calculate that energy from our inductor to be delivered to the bulb, and we'll say, so we are calculating the energy delivered to the bulb, and we'll say that energy is Wm. We use that symbol, and we say energy is normally equal to the integral of B dt, where P is power, where P equals to power, and we know power is equal to voltage times current. Now I'll say in our next step, we'll say it will be equal to VI, that is power will be equal to the integral of VI dt. But we say inductance, that is voltage, is equal to the negative of inductance di dt. So we will replace the voltage with this one, and we will say that energy will be equal to, so that negative we bring it out, and we say inductance. This is the symbol for inductance, as we have been saying. That way, di dt times, remember we had replaced v times I dt. Now dt and dt will cancel out, and we would get that energy will be equal to the integral of let's ignore this negative here. Let's ignore it for our case here. We want us to ignore that negative, and we say that it will be equal to, and we bring that inductance out because it is a constant. So this inductance, we bring it out of the integral, and we say equal to I di over I di. Let's give these limits. We say from 0 to I. Now when we integrate this part, we get energy will be equal to I, that is the inductance, I squared over 2. But when we integrate that part, that is what we get, which is half the inductance, I, that's current squared. Now, from here, but remember we have been saying that inductance is given as the magnetic flux linkage over current. Now, we wanted to replace this inductance with this one, and we say that energy, remember this is energy, so energy will be equal to, this is inductance, considering this case, times I squared. So I goes here once, goes here I times, so we should be half the magnetic flux linkage over I. Now from this is the energy that will be stored in that inductor. Now from here we can conclude, remember this is the energy for our inductors. All of the inductors we've been calculating this, they will store energy in this form, and we will conclude and say, therefore from the formula we can say energy is stored purely in terms of a magnetic field lines. And remember that is what we've been defining an inductor is and an inductance is. So we've been clearly able to see that the inductance of a material is the energy stored for by an inductor is purely in terms of magnetic field lines. Now the other part that we want to consider is the energy, the density of energy as a function. Now that energy as a the density of energy as a function, that is what we want to consider right now. The density of energy as a function. For those who have not subscribed, please, if you are enjoying the video and you find it helpful, you can just subscribe, like and comment. You can add what you wanted maybe to say in the comment section, and I will really appreciate for your support, guys. I hope we are enjoying all of us the video as we continue to learn. Remember, nobody knows everything. It is until then we learn together and we can be able to know, and we find it being helpful. Now I'll appreciate if you will subscribe to my channel. You can also tell your friends to share the same. Now let's talk about that energy, the density of energy as a function. Now we consider a cube of length. Now we'll just say consider. I'm giving the notes because I found it very helpful, because there are other guys who will be taking them as a short notes, and I will be very glad when you get clearly what I'm saying. So I should not be dictating, but less I created this channel to help you understand, and I will be doing them for all of the sciences, and I'll be doing for the lower cases and for the tertiary institutions. So we consider a cube of length dl, and having a volume of the UV. Now we take this metal cube into a magnetic field. If we put the cube into a magnetic field, and we will see that the current is going to, remember we have been saying that once we place an inductor into the magnetic field lines, there will be current being induced. Now we will say that once we place it there, there will be a current, the I will be induced. Now assuming that all the surrounding of that cube, remember this is a cube, will be having a similar case that current will be induced. So this is what I'm saying. We have a series of cubes. This is a metal cube with a series of several of them. Now we take this is the current out of the paper, and this is the current out of the paper. This will be the current out of the paper. This will be the current out of the paper. We will be seeing magnetic field lines. Remember our cube is placed in magnetic field lines. Those are magnetic field lines. Now each unit cube will be regarded as a magnetic field cell. Now each will be having inductance. So each cube will be having inductance dL equal to mu dL. That will be the inductance of each cube in that center. Remember, we can iterate this one from the previous, what we have been calculating, how we have been calculating the inductance. Now from Gauss law, we know it states that the magnetic field intensity times the dL will be equal to the current. Remember this formula, when we show it a relationship with, when we were calculating the Ampere's law, it had a relationship with the field, the magnetic field intensity. Now we will say that the energy, that is the energy that will be stored, the energy for such a cube in the magnetic field will be equal to, remember we retain the same formula that we've been saying, will be equal to this one. This will be the energy for the, once we have those cubes at the placed in a magnetic field, that will be the energy. And the energy, remember we had said, is equal to, when we were calculating the energy stored in an inductor, we said is equal to a half times inductance times current squared. This is the same thing that we have brought here. This is a half, and this is inductance. This is inductance times, that is the change in inductance. That is the, we can say this is read as we can say the change in inductance times the change in current squared. It's the same thing that I'm saying. Now we will say that energy, therefore, relating it to Gauss law, it will be equal to a half. Remember from Gauss law we said, this is what we said from Gauss law. This is the relationship, so we are going to replace the change in current with this parameters here. Those parameters, we are going to replace them. So we'll say the change in current, or we can say it is to remain. Remember, L is just the inductance of that material. This can be maintained as L as the inductance of the material. Now we replace I squared into bracket, that is H dl, we square it. Now that will be half dl times H squared times dl squared. This and this one will get is equal to half dl cubed times H squared, and this will be equal to half, this is volume, H squared. But we said our metal cube will be placed in a magnetic field lines. Therefore, we are going to say that material will be allowing magnetic field line to flow. And for it to allow it to flow, we use this mu to show that the magnetic field lines are flowing. H squared dV. Now, we can say if we divide all through, that is the energy. If we divide all through by dV, we will get the energy per unit volume, which will be equal to half, this will cancel out, half mu H squared. But we've been saying that remember when we were calculating magnetization of the material, and we derived this formula from the previous video. You can find it in the previous video that we said is equal to H. This is the formula that we decided. Now inserting, replacing our mu here, it's going to be equal to half into brackets, that is this one, plus m times H squared. Now open the brackets, it will be half mu naught H squared. Remember, I've opened the brackets. This will be equal to, H will cancel here. This is mu naught. But mu naught times this one will be equal to magnetic field lines. So which will be equal to half mu H squared plus BM, and this we can say we cancel it because this is magnetization times magnetic field lines, the same thing. So we can say will be equal to that is the energy per unity, that is energy per unity cell. Remember, a cell will be having a volume. And for today's, this is the end of our lecture today, and in the next video we are going to talk about the boundary relations, for magnetic fields. Here we will see the behavior, or what happens when we have magnetic fields being normal to the medium and being tangent to the medium. And after we have calculated that one, we will discuss about the magnetic circuit, where we will be talking about reactance, and we will be talking about permeance. And when we finish that part, we'll be heading in the right direction. Thank you guys for your time. Hope you enjoyed the video. Subscribe, like, comment, and share.